We were able to hear it, the sound in video.
I was not sure. That's why I repeat. I'm sorry for that. But let's go ahead and watch the video.
Think of it as look into the bottom of a lake, of a river, of an ocean. On land, we have a topographic survey. We survey the features on the ground. We develop contour lines for site planning, for construction, for road design. This would be doing a topographic survey of the bottom of a body of water, which we can't see. Mostly on a body of water where there's shipping. Think Lake Superior, Duluth Harbor, the Mississippi River. Wherever there's shipping, the Army Corps of Engineers wants to make sure that the water is deep enough for the boats. A marina on a lake that sediments filled in, and that needs to be dredged. So whenever there's dredging needed, you usually have a pre-survey to determine the depth of the water. You dredge out the material, you come in afterwards to measure the depths again, figure out the quantities that were dredged. Are you deep enough to where you want it to be? So if we come up to the survey site, we have our survey equipment with us and we bring a boat. We could use a client's boat and it'll take us 20 minutes to set up the whole equipment on any boat. We'll launch the boat into the water and within another 15 minutes that system is up and running. We'll typically use GPS for positioning. We have an echo sounder that measures the depth. A laptop collects the data and processes it afterwards. I pre-plan lines that I want to run on the water to come up with the coverage that I need to produce a map for various purposes. Well, local, state, federal government agencies, such as the Army Corps of Engineers, they take care of all the navigable waters in the US. Mining operations, developers, marina owners, marine contractors.
So I'm gonna stop here, and because this is a very good scene to stop at, and just to have some discussion for you. Does anybody know rod, what this thing on top of the rod close to the boat motor?
Is it a GPS?
True, this is GPS antenna. So you can see we are now doing hydrographic surveying, and this is happens for so many applications to understand the shape or the topography of the bed of the river or the sea or the ocean. So what you see here is only one technique where you have a GPS receiver, and you guys probably know by now that GPS, it communicates with satellites, and simply you're able to find the X, Y, Z, where it's at an antenna, at the antenna. But remember, the antenna is not really my interest point. Like, where is my interest point? What is the point that I'm trying to find X, Y, Z? Is it at the antenna in this picture or somewhere else?
Wouldn't the interest point be the actual bottom of the lake or whatever you're trying to survey?
Exactly. So you can see now we can get the XYZ of the antenna. However, the point of interest is falling below the antenna by one specific depth. So this system, you see only one part of it. However, there is an echo sounder, and the echo sounder is below, which simply emits a sound wave that hits the bottom of the lake and comes back, and where we can measure the depth of the water. And if you're able to measure the depth of the water, and so I think if you think about it, you should be able to find the X, Y, Z at the bottom of the lake, because GPS will give us the X, Y, Z on the top, and we're getting a delta Z, which is the depth of the water, and we can find the X, Y, Z at the bottom of the lake. You know what? This is only one technique of hydrographic surveying, and you know, you can still use total station to do hydrographic surveying. I know some of you is wondering how. Total station can find for you XYZ as you learned last year. And if my water is not deep, it's in shallow water, only in shallow water. For example, you have a small river and where the depth of the water is maybe 1 or 2 meters, then I can get my surveying rod. I can touch the bottom. I can maintain the rod to be vertical, and I can shoot all my points using XYZ. As soon as the depth of water gets large, which means bigger than or larger than the height of the surveying rod, in this case, total station cannot do it, and we will try to find an alternative technique. One of them is what you've seen on my video. Do you have any question for now? Okay, so I'm going to go back to my slide. And again, for hydrographic surveying, this is what you want to do. So this picture shows you we have a shore, and we use normal survey to find and draw contour lines on the onshore. However, offshore, we need to find a different technique. You've seen one of those techniques in my video. And simply the purpose of this presentation was nothing more than to show you that surveying is not really as simple as what you thought when you had your first year course. I can tell you there is nothing can be built without surveying. So my next topic here in our class, I have some slide. It's available on the D2L, which is a revision of total station. I know some of you will say, you know what, we had this before, so you're kind of repeating yourself, and I'm pretty sure I'm not. I am going to put everything in one perspective, and this ties into our next topic in our class, which is data processing. So total station, what it does, it simply locates one point in space. It means with the help of total station, I can find XYZ. And I'm pretty sure that you guys know what does it mean XYZ. Let me remind you. So I'm not going to do a 3D. However, I'm gonna make it things simple. I'm gonna make it 2D. So you guys know that there's something called Cartesian coordinates, and Cartesian coordinates, this your X, and this is your Y. And simply, if you have a point, let's say I have a point here, okay? So this is my point. When I say locate the point, it means I want to find the following. I want to find this point in relationship to the X, and this is called Y dimension or the Y coordinate. In addition to, I want to locate this point relative to my Y axis, and then this will be my X coordinates, okay? So again, if you expand the idea to the Z, then you will see another dimension, which is the height of the point. So this is what total station does. It finds for you the X, Y, Z of one unknown point. And by the way, if you know the X, Y, Z, then you can answer so many other questions. For example, if we know the X, Y, Z of 2 points, then we're able to find the distance between the 2 points. If we know the X, Y, Z of 2 points, we can find the height difference between 2 points. If we know the X, Y, Z of so many points, which create for us a surface, then we can find the volume to, for example, do one project. And if we know the X, Y, Z of so many points, guess what? We can come up with a map, because a map is nothing more than a bunch of X, Y, Z connected using a line work. That creates your buildings and road edges and so on and so forth. So this is what we will be doing in the next class. For now, I want you to understand that total station, it simply finds for you the XYZ. In my document here, I simply try to show you what is the history that happens before the invention of total station. It's very interesting. Please take your time and read. Really, what I want you to know is total station is not really a brand new. The first total station was born in 1971. So it's kind of 2 years older than me, okay? So it's kind of, not new equipment. Even the first version was very, very basic. I can tell you right now, and this is something you will see in my class today, that the current total station in 2020, it became so advanced, just like anything in our life. Look at the cell phone, that whenever the cell phone started, it was call and disconnect. That's it. Today, the cell phone is way, way more than it is started, okay? Now, I want to show you like how total station works, and how total station, what is the magic that can allow total station to find XYZ. Remember, XYZ on a piece of paper is not like the same as XYZ on reality. For example, if I give you this piece of paper right now I give this piece of paper and I ask you find for me the XY of this point, I think all of you will do. What you will do is you bring your scale, you measure the X, let's say 3 centimeter, you measure the Y, it will be 2 centimeter, and here we go, here is my XY. Things in surveying doesn't work this way, because simply we don't have those lines laid on the field. We cannot see where is the X line so we can measure where is the Y line. It doesn't work this way. So I'm gonna kind of quickly, I'm not gonna spend lots of time, just quickly refresh your memory about how we do that in reality. So the first step when you try to measure the XYZ, not really measuring the XYZ. The first step is to create a frame of coordinates. And we do that through points called traverse points. Please, I need confirmation. Does anybody in this class remember the word traverse? Probably I want to write it for you. Okay, here we go. So here is the word traverse. Okay, so anybody still remember from first year the word traverse? Please confirm. It takes you a little to unmute yourself and say, yes, I can remember. Yeah, I can remember about the traverse. Not much. At least I feel I'm not talking to myself.
I remember something.
Okay, so traverse, thank you so much. And traverse is simply, it's a few points, many points. It depends on the size of your area. And these points, what we do is we pick them carefully. Remember this, pick them carefully on site. So the traverse point location is not really any point on site, not random, because simply, number one, they cannot be middle of the road. Can they be? Can't be, otherwise they will be easily damaged, or maybe the person who is surveying will be unsafe. So it has to be off the road. Number two, there is a intervisibility condition. So whenever you are on top of one point, probably you need to see the previous point and the next point, because simply when we place these points on site, next is we do some measurement. And our measurement in surveying requires line of sight. It means I need to be able to see from one traverse point the previous and the next point, if you agree. So anyway, bottom line is traverse points are collection of points that we carefully pick them on site. Then once you pick the location, next is we fix them. And what does it mean fix them? It means we use some sort of tools, and it depends on the length of my project. It depends on so many factors. I can maybe start from maybe a mark on a concrete sidewalk, or maybe a nail, or maybe a piece of metal. And sometimes things become very complicated. Probably I need to make a pile which is 5-6 meters that goes into the ground to make my point very stable. Okay. Now, what is next after you carefully pick the point, and then next is you use one method to fix them on site? Here is what has to happen next. We use total station to measure a few measurements, which is number one, all the sides of the traverse. For example, I'm going to give you a simple example. Let's say here I have one traverse point and then another traverse point here. And then let's make it simple. Let's say we need only 4 points for our area. And so at each end of the line, we have a traverse point. So what to do next is we do measure all these sides. For example, from here to there, and then from here to there, and next is from here to there, and then finally we measure from here to there. So those dimensions are measured using total station, and I will share with you how shortly, because we have something in total station that allows me to measure all the lines. Next is we also have to measure all the angles, I'm going to start here. So here is one angle, and again you can see we measure all the internal angles. Now what you see is something called closed traverse, and closed traverse, you know, it's fantastic, it's very good, because simply if I have a closed traverse, then I have a way to kind of estimate and quantify how much error I have done. For example, if I measure all the internal angles, what do you think? What should be the sum of the internal angles? Please help me.
360.
Thank you so much, 360. So what if I add all the angles that I measured and it came out to be 360 degrees, 0 minutes and 30 seconds? This means I have made an error of 30 seconds in my measurement. So at least I know, and by the way, there is no way for you to go to 360. No way. It is acceptable to make some error. The thing is, we just have to limit the error, which means I'm going to put an upper limit to my angular measurement. If the error is, let's say, 1 minute maximum, and I'm below this threshold or limit, then I'm fine. And all I have to do is just go ahead and just accept this and simply go back and put back my error into my measured angles. Okay, what happens if I exceed the threshold or the limit, so my error is more than 1 minute, then in this case, I'm going to reject my measurement and I have to go back to the site and repeat them carefully. So you can see so far, all I'm doing is simply measure the angles and distances, and I will do next is after I correct all my angles and measurement. And I think you've done this last year, huh? You've done kind of AutoCAD exercise to graphically correct the measurement. I need very quick confirmation if you remember this step.
Yes.
Okay, next is remember, so far there is no coordinate system, huh? So far we have no coordinate system. Yes, we measure a figure, and this figure is the traverse. However, I haven't established yet a coordinate system. If you know about math, what takes you to establish a coordinate system? Okay, you know what? I'm gonna clean things a little bit so you guys get the idea. So I'm gonna clean all those dimensional lines just to make it a little bit clear. And now here we go. If you want to establish a coordinate system, you know what? You need an origin. So which means, you know what? I'm going to assume that the coordinate of this point is 0, 0, 0. Let's say, yeah? So that's my origin. But origin is not enough. I need a direction. So I'm going to assume my first side of traverse is my, so I'm going to say, you know what? Here is my Y. Or in surveying, you know, typically I use N instead of Y. We leave Y for mathematician and we use N for northing. And if I do that, guess what? Here is my X. So my X will be 90 degrees to my Y, forming a right-hand coordinate system. So this is my, I'm not going to call it X, because again, I'm going to leave X for mathematician. I will call this one my easting. I use E. And what happens is I can find the coordinates of these points within the coordinate system that I have just established. Origin plus one direction. So now, for example, I'm able to say, you know what? This point is, let's say, 100, 100.5, okay? And so on and so forth. So now I have a list of coordinates of all the traverse point. For example, this one will be 0, let's say 90.675, and so on and so forth. And this one, let's say, is going to be 120.123 or 125, let's say 30.156. Okay. And now, did I survey my area? So far, all I've done is I have established my traverse. And the traverse is the one that I will be using to survey anything close to the traverse line. For example, let's say I have a building. Let's say I have a building here, and this building, I'm going to give it a hatch. Okay. Okay. So this is my building. I want to locate this building in my coordinate system. Then what you will do is you go ahead and occupy a close by point. For example, this point here, probably I give it a name. So this point, let's say point C. Okay. So I will be occupying point C. And once you occupy point C, you're going to send a helper. And this helper, you guys know what he should have. The helper should have a prism, and then he's going to stand and place the prism on the corner of the building. And what I will do, I will just shoot. I will just shoot this point here. Okay. When I shoot the point, I'm going to do some measurement, as I'm going to explain in details later on. And I will finally come up with this X, how much is X here, and how much is Y, and how much is my Z. This is how do we locate point in space. Step number one, find locate the traverse point, measure the traverse, adjust the traverse, and then finally do the survey. Really, what I will do next is I'm going to show you how this guy will work, how the total station will locate for me and find for me the XYZ, and I will just take you into a mathematician, or sorry, into math. Now, before we do so, can anybody tell me what the total station is capable of measuring? So does it measure, for example, temperature? Does it measure voltage? What exactly total station can measure?
So it measures the distance, angle, and height.
Measure distance, angle, and height. Okay. Anybody else? Anyone else can tell me what is the raw measurement? I'm not saying what it can calculate. I'm saying what it can measure, like the raw measurement. And for
Location?
sure, from the measurement, we can simply estimate something. Okay. I want you guys to differentiate from now between a measurement and a calculation. So, okay, I'm going to save the time. I'm going to tell you what can it measure. So as our friend, I'm not sure who's said that, but it can measure distances and it can measure angles. And that's only it can measure. So you know, it doesn't measure anything else. Distance and angles. And I will give you more details later on. But for now, please understand, total station measures only angles and only distance, nothing else. It cannot measure elevation or cannot measure coordinates. Yes, the coordinates will be calculated later on, but not only based on the measurement of total station. And this will take us to a very, very quick discussion, which is the component of total station. You know what? Here is a short list or quick list of the component. Any total station, any, and I'm saying any, it means any, must have digital theodolite. And pretty sure that you know this name, huh? Digital theodolite or transit. And simply it measured the angles. Okay, next is we, or any total station, it has an EGM. And if you remember from last year what EGM is, it is electronic distance measurement, which means same as the tool that you buy from Rona or Home Depot, but the other one is not that accurate and doesn't measure that long distance, but the same idea. You can buy a measurement tool from Home Depot, which allows you to measure, for example, your room dimension. So very simple, you click, it has a laser beam, it hits the other side, it comes back, we can estimate the distance, okay? So that's EDM. So that's what the total station measures, distance by EDM, angles by digital theodolite. However, I can tell you, when the total station, if the total station has only EDM and digital theodolite, I can tell you, it is not really a total station. It doesn't do the job I want, okay? It needs more component because simply the whole process is digital, which means I will measure my distance, I will measure my angles, but I'm not gonna book them manually. I will not really book the distance and the angles manually. I'm not gonna write them on a piece of paper. So what has to happen is all the measurement will flow into a memory, just like the hard disk on your computer. So we need a memory to store all the raw measurement. And even if I do more than the raw measurement, for example, coordinates, I need a place or memory to store the coordinates. Now, how can you find the coordinates? You need to do some calculation, as we will see in few minutes, because simply angles and distances are not coordinates. Angles and distances are not coordinates, and this is obvious here. Look at this. So you can see here in this example here, I am finished already my traverse, all the angles and all the distance, and there is no coordinate until I say, you know what, here is my north, here is my 0, 0, and here is my east. Then I can find X, Y, Z. So angles and distances are not coordinates. We need to do further calculation. And you guys know, what can we use to do some calculation? It is something on your laptop called processor. Processor, okay? So we need a processor, and the processor, what it does, it simply combines all your measurement in some mathematics and create for you coordinates. If you guys remember, on number 5, there's something called input and output devices. When I say keyboard and display, if you guys remember from last year, we need interaction with total station. So the user will not just shoot the point and that's it. No, there is some time where the user will have to input something, and sometimes where the user will have to retrieve something, and we need something to input and output in my total station. So any total station must have a keyboard, must have a display. It is not optional. It is not optional. And then finally, number 6 here on my list, for sure, we need something to communicate my data. Once you finish the survey on site, looks like we need to take the data and then transfer the data into my laptop or my PC to do further calculation. And there are so many ways to do that, starting from a simple cable that hooks your total station into your laptop or PC. And then recently there are few advancements, like for example, Bluetooth and infrared and SD card and SM like data. So there are so many ways to be able to take the data from total station and transfer it over to my laptop or PC. And of course, there is one component probably I've never mentioned, but probably you can guess. It is probably number 0. Can anybody guess what is number 0? It's kind of tricky, huh? What is number 0?
Stand.
For sure, there must be a tripod, but there is something. If it doesn't exist, then simply nothing is gonna work.
Humans?
For sure. But I'm talking about the battery. If there is no battery, remember the EDM, it simply uses energy. So if battery is, you can say the battery is number 0. I didn't put it here. You know, probably it's a mistake. I don't know, but it's battery. I want everyone to understand that battery is not optional. We must have battery to operate the ATM and also the digital theodolite. Now you know the component of total station. You know the component, but now I'm gonna put things in perspective and show you how this thing will work. Okay, let's be clear before we start. Let's be very clear. Total station can do only 3 measurements. Only 3 measurements. And the 3 of measurement are listed here. So here is 1, and here is number 2, and here is number 3. As you guys said, it can measure a distance, but let's be specific, because distance, it can be a slope distance, or it can be a projection of the distance, can be horizontal. Okay, so let's make it clear. A total station measures a direct or slope distance between total station and the center of the prism. Okay, so in addition to the slope distance, it measures angles. And in surveying, there are only 2 types of angles. Only 2 types, not 3. One is called a vertical angle, and the other one is called horizontal angle. A vertical, horizontal. That's it. So maybe in math, there is something called spatial angle, which we don't care in surveying. We only measure a vertical angle in a vertical plane, and we measure horizontal angle in a horizontal plane. And those are only measurement. Total station cannot do, and I'm very clear, cannot measure anything beyond those 3 numbers. That's it. Now, you will see those 3 numbers are not sufficient to find X, Y, Z. We need to have some inputs from the user. I'll give an example, and we will start seeing this right away. But let me show you this 3D picture. It is very descriptive, and it tells you what's happening. So please look at my screen. I kind of try to came up with a 3-dimensional picture. And then I know sometimes for some of you, 3D is fun, but we need to simplify it to come up with equations. So let's look at the 3D, and then I'm going to show you the other views. So in 3D here, I have point A and point C. So point C is simply a traverse point where I have total station. Remember, I wrote here a statement, and I said here, I'm not showing the tripod or total station, and I'm also not showing the prism. Okay, I'm not showing the rod or the prism or the tripod for clarity. So I removed the tripod. I removed here the rod. So this point in green is the center of the prism, and this point here is where the ADM laser beam goes. Okay, so this point here is your traverse point, and this point here C is any point on site, which can be building corner, it can be electrical post, it can be any feature point on site. And remember, my goal is to find where the point C in space. What is the X, Y, Z of my point C? Again, point C can be any point of unknown coordinate on site. Now, when we establish a line of sight, and what's the line of sight is here. This is in blue, is the line of sight that goes to the center of the prism. Then I hit enter on my keyboard. What happened is total station can measure 3 things. Let's confirm. One is the slope distance, not horizontal distance. Number 2 is the vertical angle. Please take a moment and try to understand the vertical angle is measured from the horizon to the line of sight. Number 3 is, which is here, this is a horizontal angle, an angle measured in horizontal plane, which is NE plane. Okay, now I know 3D is fantastic. It helps us to understand. I will remove my arrow so you guys can take a better look. Please take your time to understand what's happening. Then to create and come up with some math equation is very difficult to look at this picture here. Now what I will do is I will show you 2 other views. Number 1, I will simply take an elevation view between point A and point C and see what happens. Next is I will do a plan view, and those views will help us to come up with mathematics to find the XYZ of point C. Okay, are you ready? Let's move on to our first view. So I'm going to switch back and forth for maybe a couple of times. I want you to correlate between the elevation view here and this 3D. So this one is generated by looking in this direction between A and C. Okay, here we go. This elevation view, it helps us to find this unknown. Remember, don't forget, please, that our objective is to find the elevation of point C as part of the three-dimensional coordinate. Remember, I want to find the easting of point C. I want to find the northing of point C. I want to find the elevation of point C. Okay? Now, how to find the elevation? Please, you need to understand, here is one measurement, this SD, and here is another measurement, which is called V sub C, which is the vertical angle. I want to ask you a simple question. Total station can do only those, and that's it. Can measure SD, can also measure VC. Anybody good at math to look at this geometry problem and tell me, can I find the H of C if total station can measure SD and VC? And remember that when I finish my traverse, I'm able also to find the coordinates of point of the total station of, so this point here is a traverse point, huh? So I know the X, Y, Z or easting, northing elevation of the traverse point. So please, anything that I mark with the arrow, this one, think about it as something you measure or you know. Is that sufficient? What I have so far, SD, VC, and HA, is it enough to find the height of point C above mean sea level? Please say yes or no.
Yes.
Okay, if you said yes, please tell me how. I'm gonna write after you. Give me the equation.
Well, I just know you have to find the long side using trigonometry, your triangle, and subtract it with HA.
You know what? I mean, I'm gonna follow you. Listen, so what you said is, I think, what this is, you know what? Let's look at this triangle here. We have a triangle where we have the diagonal SD. So this is a number, let's say 100 meter, and see, and then we simply measure the vertical angle, and let's say the vertical angle is 5 degrees. So if we go ahead and multiply the SD, multiply by the sine of the 5 degrees, this is what you get. You get the direct dimension from here to there. Would you agree?
Yes.
Okay. But by the way, when you think about it, please, and I'm going to make it in red here. If I now is able to estimate the V, okay, capital V, and I have the HA, is there anything else missing that I must measure and feed in the total station to give me the HC? By the way, it's already on my slide. It's not an invention. There are something missing already. Okay, I'll give you help. What do you think about the instrument height?
It should be given. We know.
Is not given, sir. It's not given. Be careful about your language. It's not given. Who is going to give it to you? You.
Well, we measure on site when we put the tripod.
Exactly. Thank you so much. Is it Lucas?
Yes.
Thank you so much. Yes, we measure it. So we use our measure tape. We measure the instrument height, and then we feed the instrument height into total station. What else? What do you think? What else on the same picture? Okay, I'll help you out. It's on the other side. So on the other side here, there is RH, which is a reflector height. So a reflector height is also, we need to measure and feed to total station before we hit enter. Remember, this is one time, because as soon as the setup is the same, so HI doesn't change until we move total station. So this one measurement, but potentially the reflector height maybe can change between one point to the other point. You must enter reflector height before you hit enter. Otherwise, if you have a wrong reflector height, then the elevation will be wrong. Okay, finally, how can I find my HC? Here is the equation. Okay, I'm going to box it out, which is not very difficult. So the HC on the left side, HC, point of unknown, is equal to the elevation of point A, which is a control point, traverse point of known elevation. You add to that instrument height, and then you add to this SD multiplied by sine the vertical angle, which gives you the V, and then finally we subtract RH. Now, if you think about it, you look at the signs, like why do we have to add IH and why we have to subtract RH, okay? So you can see always the total station where the laser beam goes along the line of sight, it's always above the point, the control point, always above, unless you're Batman, okay? So always total station is above the point on the ground. So that's why we always add IH. However, in most cases, the point of interest, I want to be clear, where is the point of interest? This is the point of interest. It's the point on the ground, Center of the prism is not the point of interest. However, you can see there is a vertical offset between the point of interest and the point of, the center of the prism and the point of interest. And that's why, look at this. The point of interest is falling below the center of the prism. And that's why we need to subtract RH. And by the way, this is most cases, 99% of the cases, the point of interest is on the ground where you need, where it's RH below center of the prism. In few cases where you want to find the elevation of the underside of the slab, or let's say the ceiling, okay? I'm gonna probably draw a section for you. So let's say you are in a room, and let's say this is the floor of the room, and total station is here, okay? Here is total station, and your point of interest is here. Somebody asks you, can you please find for me the elevation of the ceiling? So what you will do is you place your prism upside down. So here is the center of the prism, and then you shoot the center of the prism here, and simply you can see the point of interest is above the center of the prism. And what happens here? This equation will be plus RH, because at the point of interest, which I want to find XYZ, is above, which means I have to add the reflector height to find the elevation of the underside of the slab or the ceiling, okay? One last thing before I give you a break is that let's look at VC. Okay, so guys, vertical angle. Vertical angle is the angle from the horizon up to the point or low to the point. So the vertical angle, sometimes it can be 0, sometimes it can be 5 degrees, 10 degrees, 20 degrees, maximum of 90, and that's only theoretical. However, it can also be below the horizon. So we have a depression angle, and it can be minus 5 degrees. For example, if I have a situation, I'm on the top of a mountain and I'm shooting a point in the valley, you can see my line of sight is below the horizon. And if my line of sight is below the horizon, think about it, you will see the vertical angle is negative, minus 5 degrees. Now, here is my question before we break. If my vertical angle is negative, should I change this equation, or my equation stays the same? What do you think?
It stays the same, just that the value is in negative, so it would.
Thank you so much, and I want everybody to have the same belief. So exactly as I think Lucas said, the vertical angle doesn't change the equation, even it's negative. Really, the sine function or the cosine function, those are smart function, which means if you have a negative angle, like a depression angle, simply the sine will know and feel it, and the sine, it comes with a negative value. So when you do the manual calculation, very simple, don't change the equation. The sine of minus 5 degrees is equal to minus sine 5 degrees. So on your calculator, you will go ahead and say, you know what, plus 200 meter for SD multiplied by sine minus 5 degrees, and simply the sine will take care of changing the sign. Okay, I mean the the sign in the front of SD. So please take a note that we do not change the equation. And by the way, this equation, it is already built in total station. It's built in, which means anytime you measure a point, simply total station, the microprocessor will simply take all the measurement plus the input, will input the HA, the input is IH, the input is RH, and simply combine all of them and gives you the H of C. Now, I know some of you will ask right now, what happens if my, go back to the same problem here. What happens if I am measuring a point underside of the ceiling? Okay, the underside of the slab or the ceiling. How can I change this equation if you just told me that it's built in? No one can change it. Any help? If I'm doing this business here and I'm measuring point to the underside of the slab.
We can change the minus RH to plus RH.
You cannot change it. You cannot change this equation in the total station. All you have to do is input the RH in the display with a negative value. So for example, if this 1.3 meter, when you input this number on your screen, you input minus or negative 1.3. And simply because you input minus 1.3, you can see here by mathematics. So you say, like so, you will say negative and then negative 1.3. So you will end up adding the RH to your equation. Okay. So whenever we measure a point to the underside, whenever our rod is upside down, then we input the RH by negative value. Any questions so far? Okay, if there is no, go ahead.
What is the role of horizontal angle? Like how we use it?
Excuse me, say it again.
For the horizontal angle, how we use it?
You know what? Like this is my discussion after the break. So after the break, remember to generate the elevation, we looked this way. So we looked this way to find elevation. If we want to find the easting and the northing, we simply have to put our eye here and look from this direction. And this will take us to this drawing here and this plan view, and this will be after the break. So please be patient until after the break, and you will see how do we estimate the easting and the northing after the break. Any question for now? If you have no question, then I will break for 10 minutes and I will see you guys sharp at 11. Thank you so much. We'll stop the recording right now.